You and 5 of your family members run the town's most famous burger store, and it's all thanks to one thing: your incredible, mouth-watering secret sauce. But there's one problem. People are desperate to steal the recipe. And right now, the entire thing is in plain text. If anyone was to steal it, they'd have the whole recipe and it's over for your family's burger business. The 6 of you gather around the table to solve this urgent problem. How can we protect the recipe from falling into the wrong hands? Your little brother is the first to propose an idea. We should encrypt the recipe using a secret key and a solid encryption scheme, he says. Even if someone steals the recipe, they won't be able to read it because they don't have the key. People nod, but your uncle looks perplexed. Wait a minute, if we encrypt the recipe, then how are we supposed to read it? I need to make this sauce perfectly, to the letter each morning. Don't worry, your little brother responds. We can each have our own copy of the key. That way, any one of us can decrypt the recipe whenever we want to make some sauce, and encrypt it again once done. Everyone seems convinced, except for your granddad, the renowned creator of the sauce. Everyone having the full key, huh? I can see a big problem with that, he scowls. It only takes one person to lose their key or leak it, and my recipe is done for. It's too risky. We need a way where no single person can ruin the secret. Your dad speaks up. What if we split the key into 6 pieces and give one piece to each person? If someone's key part gets leaked, it carries no risk because it's only 1/6 of the key. But the 6 of us can still decrypt the recipe by simply combining our key parts together. There's nods of agreement around the table. Except this time, your mum finds a problem. That is totally impractical, she says. So you're saying every time we want to make a batch of sauce, we need to have a whole family reunion just to get the full key back? And what if someone loses their piece of the key, or is on vacation for the weekend, or runs off and leaves the family business? We wouldn't have all the key parts required to decrypt our own recipe. Ideally, what we want is this. We want a way to get the full key back if a certain number of us, say any 4 of us, brings our parts together. Everyone starts sweating. The problem at hand seems impossible. As the meeting goes on, you hurriedly take notes of the minutes. We need to encrypt the source recipe with a secret key, so anyone who steals the encrypted recipe can't read it. But giving the full key to each person is too risky because one traitor equals game over. Fragmenting the key into 6 parts and giving one piece to each person has no room for error. One person losing their part means we can't reconstruct the original key and we are locked out of our own family recipe. How embarrassing. So we need a system where each family member gets some kind of piece of the key, but not the whole key, just a piece which can't decrypt anything on its own. The original key is recoverable if any 4 family members unite their key pieces. But a group of fewer than 4 family members can't recover the original key or even gain any information. I emphasize the any in any 4 family members because that rules out splitting the key into 4 parts and divvying those. By the pigeonhole principle, some people would end up with the same key part, so this does not guarantee that any subset of 4 can recover the original key, since the subset may not have all the unique parts needed to reconstruct it. We need something a bit smarter here. 4 or more reconstructs the key and unlocks the source. Fewer than that, learn nothing. Pause the video now to take some time to think about the problem. This is Shamir's secret sharing. In this scheme, you can split a secret such as your key into n parts called shares. Then you pick a threshold k such that k or more people can combine their shares and reconstruct the secret, but less than k shares are completely useless. In your case, there are 6 of you, so we would create 6 shares and give you all 1 each. And you want to recover the secret key if any 4 of you combine your shares, so k equals 4. But this scheme is not just for family burger businesses. You can use it to hide any secret amongst n people, and reveal it again when k of those people come together. Of course, as long as k is less than or equal to n. Let's build up a visual picture of how the scheme works. If I arbitrarily draw a point on the xy plane, say at 1, 2, how many straight lines can we draw through this point? For example, we can draw y equals x plus 1. We can make it steeper, y equals 3x minus 1. We can even go downhill, y equals negative 2x plus 4. In fact, there are infinitely many straight lines we can draw through this point. Why is that? This is the general equation for a straight line. It's a degree 1 polynomial because the highest power of x is 1. We want this line to pass through our point 1, 2, so let's plug that in and simplify. We have one equation but two unknowns. There are infinitely many A-B pairs which satisfy this. The conclusion, 1 point alone is not enough to uniquely determine a straight line. What if we plot a second point, 2, 6? Now how many straight lines can we draw that pass through both points? Actually, it's only one. This is easy to see visually, but let's convince you with the algebra too. Again, here is the equation of a straight line, but this time we want it to pass through both points. So sub both points in and simplify. There are two unknowns, but this time there are two equations. You can solve these equations simultaneously to find a unique solution for A and B. Have a go yourself. And so this leaves only one line that passes through the 2 points. A degree 1 polynomial requires 2 points to uniquely define it. Why don't we extend the question? Here are the same 2 points. Now how many parabolas or degree 2 polynomials can we draw through these 2 points? Remember, a degree 2 polynomial means the highest power of x is 2, i.e. x squared. Here's one. But wait, here's another one. I can even flip it upside down. In fact, there are infinitely many parabolas passing through these 2 points. That's because, algebraically, we have the same problem as before. Here is the general equation of a degree 2 polynomial. Now we want it to pass through our 2 points, so sub them in, and simplify. This time we have 2 equations, but 3 unknowns. This system is underdetermined. There are infinitely many solutions for A, B, and C, leaving infinitely many parabolas. But at a third point, say at 3, 4, now how many parabolas, degree 2 polynomials, can we draw through all 3 points? Now, it's only one. A degree 2 polynomial is uniquely determined by 3 distinct points. And remember, a degree 1 polynomial, a straight line, was uniquely determined by 2 distinct points. Can you spot the pattern? A degree D polynomial is uniquely determined by D plus 1 distinct points. For example, with these 3 points, there are infinitely many cubic functions, degree 3 polynomials, which pass through them all. But as soon as we add one more point, a fourth, the cubic slots into place. Your uncle is a bit bamboozled. What the heck does this have to do with the source? Remember the goal of Shamir's secret sharing. We want to split a secret into n shares such that k or more shares can recover the secret, but fewer than k shares are completely useless. We just learned that a degree D polynomial is uniquely determined by D plus 1 distinct points. Let's exploit this property by picking a degree k-1 polynomial. First, embed the secret key into this polynomial by making it the y-intercept or constant term, i.e. when x equals 0. Next, pick n distinct points which lie on this polynomial. These are our shares and we give 1 point to each person. Each person must only know their own point. Amazingly, the original polynomial, and hence the secret key, is only recoverable if any k or more people bring their points together. Let's do a walkthrough. In our example, we have 6 family members, so n equals 6, and we want the secret key to be recoverable if any 4 family members combine their shares, so k equals 4. We need a degree k-1 polynomial, so we need a degree 4 minus 1, or degree 3 polynomial. Let's choose, say, x cubed minus 2x squared minus 20x plus 64. Your secret key is the y-intercept. This occurs when x equals 0. In other words, you'd embed your secret key, 64 in this case, into the constant term. Now it's time to create the shares. Pick any 6 points which lie on this polynomial, one for each family member. Let's choose 143, 224, 313, 416, 539, and 688. Each family member only knows their own point. Now, if any 4 family members puts their points on the plane, we can reconstruct the original degree 3 polynomial. Then we can recover the secret key by simply checking the y-intercept, plugging in x equals 0. But if fewer than 4 family members combine their points, there are infinitely many degree 3 polynomials which can pass through these points, and infinitely many y-intercepts, or potential secret keys. These points are useless. Let's randomly create this degree 3 polynomial, says your little brother, who's pretty tech-savvy. But wait, how can we ensure the computer is precise enough to represent these coefficients and shares? He makes a good point. If we randomly generate the coefficients and shares, theoretically there are infinitely many real numbers we can choose as coefficients, and infinitely many points on this polynomial we could pick as shares. But computers don't really work with infinity. Every number has to be represented in a finite number of bits. For real numbers, this can lead to rounding errors, and if each point is truncated, even only slightly, it could lead to an incorrect polynomial being reconstructed and an incorrect secret key. Here's a little demo of this. I randomly generated a degree 1 polynomial, a straight line. Of course, the secret key is the y-intercept here. I then randomly generated 4 shares, but when I brought different combinations of 2 shares together to reconstruct the line, I got slightly different values for the secret key each time. If we are using the secret key for encryption, it needs to be completely accurate, and actually I think none of these match the original secret key. A natural idea you might think of to address this problem of computer representation could be to only use integers. Choose integer coefficients in the polynomial, that is, the numbers before the x terms, and choose integer x values for the shares. Then the y values of the shares will come out as integers too. That way, there are no more rounding errors, so reconstructing the polynomial to get the secret key back becomes reliable. But your grandpa again is skeptical. Hold on, you said before that if fewer than k shares are combined, those points are completely useless. Each possible value of the secret key should still be equally likely. But if you now restrict the polynomials to use integer coefficients, could that rule out some potential keys and leak information? Actually, he's right. Our idea to use only integers has a flaw we can't ignore. Let's take our degree 3 polynomial from earlier. The secret key is the y-intercept 64. Previously, we saw that 3 points could have infinitely many degree 3 polynomials passing through them, yielding infinitely many potential secret keys. But now, we have restricted ourselves to using integer coefficients only. This rules out all secret keys that came from polynomials with non-integer coefficients, leaking some information. Our secret key can only be certain values now: 46, 40, 34, 28. So what's going on here? What information is being leaked exactly? Well, here is the equation of a degree 3 polynomial. The secret key is the y-intercept or constant term, which is d in this formula. Now suppose an attacker stole these 3 points, which is less than the k equals 4 points we need to reconstruct the polynomial. Sub all these points into the equation and simplify. Now we have 3 equations and 3 unknowns. Let's eliminate 2 of these variables, say b and c. When we were working with real numbers, there were infinitely many AD pairs which could satisfy this. But this attacker is smart. They know that the coefficients a, b, c, and d now have to be integers, so if we sub in integer values of a only, we can see a pattern emerge for the potential values of d, the secret key. Firstly, the secret key must be even, since any integer value of a we sub in yields an even value of d. And even worse, we see that each possible value of the secret key is 6 apart. We need to tweak the scheme so that fewer than k shares don't leak any information about the secret key in this way. Each secret key should still be equally likely, even as the attacker gains more shares. And we want to prove it too. Enter the finite field, the final piece of the Shamir's secret sharing puzzle. This is the number line. It extends infinitely in both directions. Now imagine we live in another universe where the only numbers we have are integers from 0 to 6. In this universe, if you want to add 2 numbers, say 4 plus 3, the answer is not 7. We wrap back around to 0 again. Similarly, if we want to subtract 1 from 0, we don't dip into negative numbers, we wrap back around to 6. In this sense, the number line in this universe can be thought of like a ring. But how can we keep all the numbers contained to the integers 0 to 6? For example, I can think of a number outside this range, say 12. We use what's called modular arithmetic, in this example, mod 7. Mod just means divide and take the remainder. For example, 12 mod 7 is 5, because 12 divided by 7 equals 1, remainder 5. 12 is congruent to 5 in our mod 7 universe. Each integer can be squished into its mod 7 counterpart by dividing the number by 7 and checking the remainder. As a result, we can do addition and subtraction and even multiplication and keep all numbers in this 0 to 6 integer range. For example, 6 times 4 is 24, but when working with mod 7, it wraps around to 3, because 24 divided by 7 has a remainder of 3. And when the modulus is a prime number, like 7 in our example, even division works. Consequently, this forms what's known as a finite field. We have a little bubble where addition, multiplication, and their inverses, subtraction and division, are all possible, but the elements of this world are confined to the integers 0 to 6. And this is the kind of world we want to make Shamir's secret sharing information theoretically secure, only maybe a bit bigger than mod 7. Here's how we adapt Shamir's secret sharing to use a finite field. This time, we start by picking a large prime number, p. Your prime has to be larger than n, k, and your secret. In this example, we are going to use 7 to keep the math simple, but in real life, you'd pick a much larger one. Then all the remaining steps are the same. We still choose a polynomial of degree k minus 1, and we still generate n shares by picking n points on this polynomial. The only difference is everything is now calculated modulo p. Let's start with the polynomial itself. This time, you'd now randomly select the k-1 coefficients from your finite field. The equation of our polynomial becomes x cubed plus 5x squared plus 2x plus 3. And any output of this graph should also wrap into the range 0 to 6 using mod 7. Divide each y value by 7 and take the remainder. Next, our finite field only contains integers, so we should grey out all the points when x is not an integer. These points now show where it's defined in the finite field. As always, make the constant term of the polynomial equal to your secret key. That is 3 now. Now for the shares, again select integer x values from our finite field too, excluding x equals 0 since that's where our key lies. But this time when we calculate the y values of the shares, anything that spills outside our 0 to p minus 1 box gets wrapped back into it with mod p. In our mod 7 example, try plugging 1 into the polynomial to find the y value of the first share. You'd get 1 cubed plus 5 times 1 squared plus 2 times 1 plus 3 equals 11. But modulo 7, that's just 4. The point 1, 4 is our first share. Have a go at finding the remaining shares to give to each family member. The rest of the scheme is the same. K or more shares can recover the secret key, and fewer than k shares cannot. So, what was the point of this little finite field adjustment? A few reasons. Firstly, computers can represent integers perfectly, and everything in our finite field is an integer. Reconstructing the secret key becomes reliable. Secondly, using a finite field keeps all shares in the range 0 to p minus 1. Programmers rejoice at this because we know for certain that we won't get incredibly large values that our computer can't represent. For example, what if we wanted the secret key to be reconstructed if 101 people combined their shares? We'd need a polynomial of degree 100. Without a finite field, our computer would run out of bits to represent the shares. But with a finite field, these monstrous values get wrapped back into a reasonable range. But probably the most delightful benefit of using a finite field in Shamir's secret sharing is that it guarantees the scheme is information theoretically secure. This ensures that even if an adversary finds fewer than k points, he gains absolutely no information about the secret key. Each secret key is still equally likely. This wasn't the case when we used regular integers. Remember, some information about the secret key was leaked as attackers found more points. In this finite field, modulo p, having k minus 1 shares gives an adversary no more advantage than having 0, and we are going to prove it. Whoa, 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 hold your horses, says your mum. Before we prove anything, I think we're missing a pretty important step of the process. You say if any four of us brings our points together, we can reconstruct the original polynomial and get the secret key back. But, how? Do we really just plug our 4 points into the general equation of a cubic and solve simultaneous equations for hours? And how do we get the solution using modular arithmetic? What if I told you there's a really elegant shortcut? We can derive a formula for the original polynomial without needing to go to all that effort of simultaneous equations. It's called the Lagrange interpolation formula. Suppose we bring 4 points together and we want to find the unique degree 3 polynomial which interpolates these points. Our goal is to reconstruct the original degree 3 polynomial where these 4 points all lie on it, i.e. plug in 1 and you should get 4. Plug in 2, you'd get 0. P4 equals 1 and P6 equals 5. We will build it by adding 4 parts together, one for each share or point. Now the idea is that if you plug the share's x values in one at a time, it activates a different part of the polynomial and deactivates the remaining parts. For example, if I plug in 1 from the first share, I want to light up the first box and get the expected y value, 4, and deactivate the remaining 3 boxes to get 0. This leaves a value of 4 overall, our expected output. Similarly, if I plug in, say, 4 from the third share, I want the third box to activate and output 1, and the first, second, and fourth boxes should be deactivated and contribute 0. To achieve this, let's start by deactivating the boxes we don't want. Let's start with the first share, 1, 4. We want the second, third, and fourth boxes to output 0 when x equals 1, so they don't contribute to the output. This can be achieved by putting an x minus 1 factor in those parts. Plugging x equals 1 into any term with an x minus 1 factor simply gives 0, and those entire terms disappear. Similarly, plugging x equals 2, the second share, into the polynomial should deactivate the first, third, and fourth boxes. So how can we do this? Well, this can be achieved by multiplying these terms by an x minus 2 factor. Same story for the third share and the fourth share. We have this polynomial so far now. This is good progress. Now when we input the x value of a share, say x equals 6, only one term is switched on, i.e. gives an output. The rest turn to 0. The first 3 parts become 0 when 6 is plugged in, thanks to that x minus 6 term, so we can focus solely on the last term. But hold on, we want this last term to output the share's y value, 5 in this case. Annoyingly, there's already some factors in there from deactivating the other shares. When we plug 6 into this, it gives some other number, 40 in this case. For the next stage, let's control the output of the activated term to give the desired y value. Let's take a look at this final term again. We can divide the term by what it currently evaluates to when you plug x equals 6 into it to normalize that whole fraction. In other words, we would divide by 6 minus 1 times 6 minus 2 times 6 minus 4. Now when we input 6 into this term, the numerator is the same as the denominator, so it outputs 1. Finally, we can simply multiply the whole term by 5, our desired y value. To show the big picture again, plugging 6 into any of these first 3 terms gives 0, and this final term gives 5, our expected y value. So 6, 5 lies on this polynomial. Let's do the same for each other share's piece. First, we normalize the existing term for that share's x value, then multiply by the expected y value of the share. The result? Our polynomial which interpolates these 4 points, just rearranged. No simultaneous equations required. Isn't that beautiful? Here's the formula in all its glory. Firstly, we loop through each share from 1 to k and create each term which we add together. For the current share I, we multiplied the whole term by the y value of that point. Then we created that fraction. So for each other share, j, we put that x minus xj factor in the numerator. This was so that when xj is plugged into this term, i.e. the x value of a different share, it gives an output of 0. This is to ensure that this term only gives an output for xi, the current share. Then in the denominator, we normalize the fraction. So big picture, the value of the fraction is 1 when xi is plugged in, and 0 when any other share's x value is plugged in. And this is performed to make each term, then the terms are added together to create the polynomial. Okay, and the secret key is the y-intercept of this polynomial. So we can simply plug in x equals 0 to recover the key, right? Says your dad. Let's see, hold on. This comes out as 64 over 5, but from earlier our secret key was 3. Something's off here. That is because 64 over 5 is the value we'd get in our normal real number arithmetic. But remember, we're working in our mod 7 finite field now, so we need to learn how to divide in modular arithmetic to compute this fraction, the final step to calculating the secret key. Let's think about division in the real numbers. We know that dividing by a number is the same as multiplying by its reciprocal. For example, if we want to divide by 5, that is the same as multiplying by 1 over 5. So what is special about a number and its reciprocal? They multiply to give 1. For example, 5 times 1 over 5 equals 1. Division in modular arithmetic can be defined using a similar approach to this. When we want to divide by a number, we actually multiply by the multiplicative inverse of that number, mod n. And how do we know what the multiplicative inverse is? The original number multiplied by its inverse is congruent to 1 mod n. Just like how 5 times 1 over 5 equals 1 in the real numbers, 5 times its multiplicative inverse mod n is also 1. Let's do an example to see if you get it. What is 3 divided by 2 mod 7? This is the same as 3 times the multiplicative inverse of 2 mod 7. So let's find the multiplicative inverse of 2. In other words, find which number, when multiplied with 2, is congruent to 1 mod 7. 2 times 1 is 2, which is congruent to 2 mod 7. 2 times 2 is 4, which is congruent to 4 mod 7. 2 times 3 is 6, which is congruent to 6 mod 7. 2 times 4 is 8, which is congruent to 1 mod 7, because 8 divided by 7 has a remainder of 1. Found it! The inverse of 2 is 4 mod 7, because 2 times 4 is congruent to 1 mod 7. So back to our original division, to perform 3 divided by 2, we instead compute 3 times 4. And this is 12. Then mod 7, remember, divide by 7 and take the remainder. This is congruent to 5. Now you get it. Let's do our original fraction, 64 divided by 5, to find our secret key. First, find the multiplicative inverse of 5. 5 times 1 is 5, which is congruent to 5 mod 7. 5 times 2 is 10, which is congruent to 3 mod 7. 5 times 3 is 15, which is congruent to 1 mod 7. So the inverse of 5 is 3. So to calculate 64 divided by 5, we should instead compute 64 times 3, which is 192. This is congruent to 3 mod 7. We've gotten our secret key correctly. As a side note, this is the reason why our modulus needs to be a prime number like 7. In a finite field, every number has a multiplicative inverse, except 0 of course, so division is well defined. All we need to do is multiply by the multiplicative inverse. If our modulo is not prime, not every element has a multiplicative inverse. Can you work out why? Your granddad, being the most protective of his recipe, wants an explanation of the scheme's security. We know very well now that a degree k-1 polynomial requires k points to uniquely define it. Let's take this and build on it. If we have k points, there is exactly one polynomial of degree at most k-1 which interpolates or passes through all these points. Take our finite field and suppose the attacker has k-1 points or shares. It may not be enough information to recover the secret key, but can they uncover some information about the secret key? the y-intercept of the polynomial? They can't. Suppose they guess a secret key, they are essentially choosing a possible y-intercept, which is the same as adding one more point. So they now have k points total, and there is exactly one valid polynomial that interpolates the guess point plus the k minus 1 points from the shares. And this is the case for all p secret keys they could try in the finite field. Each one results in exactly one valid polynomial that fits the k minus 1 shares plus the guess secret. This means each secret key is equally likely. The attacker learns nothing. What if the attacker has even fewer points, say k minus 2 points? The attacker still can't narrow anything down. There are just 2 degrees of freedom now. In other words, for each guess of the next share, every possible secret key is still just as valid. This is thanks to the finite field. Earlier, when we used real numbers but restricted our polynomials to using integer coefficients, we leaked some information because attackers could rule out any y-intercepts or secret keys which did not emerge from a polynomial with integer coefficients. But now, in a finite field, everything, including the secret key, is an integer from 0 to p minus 1. So every y-intercept in the field corresponds with a valid polynomial within the field, no ruling out anything. It's almost like rather than adding constraints to our real numbers, which could leak information, we just changed our field entirely. Isn't that cool? But there is one thing left outstanding, the lemma itself. We claim that if you have a set of k distinct points where no two x values are the same, then there is exactly one polynomial of degree at most k minus 1 which passes through every point. But where's the proof that there is exactly one? This is important to prove because it leads to each potential secret key in the field being equally likely. Information theoretic security. Firstly, we know there is at least one by construction. We can simply use the Lagrange interpolation formula from earlier in the video to make a polynomial that works. Let's call this p of x. But how do we know that p of x is the only valid polynomial which interpolates the points? Suppose we have another degree k minus 1 polynomial, q of x. And suppose, leading to a contradiction, q of x passes through the same set of k points as p of x. Think about the difference between these two polynomials. R of x equals p of x minus q of x. In other words, at every x value, just subtract the y value of q of x from p of x. This new polynomial, r of x, must also be of degree at most k minus 1. Since we are only subtracting 2 degree k minus 1 polynomials, we aren't bringing in any higher power of x. Now, what would be the roots or zeros of r of x? R of x is the difference between p of x and q of x. So for any x value where this difference is 0, there will be a root of r of x. Now, when is the difference between p of x and q of x 0? Well, anytime the two polynomials intersect. We assumed at the start that p of x and q of x both pass through the same set of k points. So at each of these k points, the difference between p of x and q of x is 0, and we can mark these points as roots of r of x. This means r of x has at least k roots. But hold on, by the fundamental theorem of algebra, a non-zero polynomial of degree k minus 1, like our r of x, can't have more than k minus 1 roots. So the only way for r of x to have these k roots is actually if it is the zero polynomial, i.e. r of x equals 0 for all x. And if r of x is equal to 0, but r of x is also equal to p of x minus q of x, this implies that p of x minus q of x equals 0. So p of x equals q of x, which proves the uniqueness. There is only one polynomial of degree at most k minus 1, which passes through or interpolates k points. Back to the big picture, every set of k points or shares has exactly one valid polynomial which interpolates it, leaving each secret key equally likely. The scheme is information theoretically secure. Everyone in the family is delighted with this scheme. The next morning, your mum, dad, brother, and yourself all wake up early to greet the new day with a new batch of sauce. Using the Lagrange interpolation formula and modular arithmetic, You all combine your key shares and recover the secret key. Then you easily decrypt the recipe to cook up some yummy sauce. There was no need to wake your grandpa, who is still sleeping peacefully, knowing his secret sauce is protected with the power of maths.